Hi everyone, my name is Wenzel Jakob and I'm really honored to give this keynote at High Performance Graphics, so thank you very much for having me. In the last years, my group has really dedicated itself to the problem of differentiable rendering, and today I'll share some of the things that we've learned along this journey. And this is our agenda for today. I'll start by giving some intuition about the kinds of problems we're trying to solve, and I'll show several demos to convince you that this is in fact a really important problem with applications in many different areas. And then we'll introduce a simple example problem and use it to really explain differentiable rendering and some of the challenges that this involves, like how to do it at all, how to differentiate efficiently and deal with discontinuities, and how to make it robust. So let's get started. When we run a rendering job, we have to provide it with certain inputs like the positions and shapes of objects, the materials, light sources, and so on. And after crunching the numbers for a while, it's going to produce an image. Now, in the rest of the talk, we'll think of this whole process as simply evaluating a function, where the scene description, x, is just a long vector of numbers, potentially with millions and millions of entries, and the same is also true for the generated image y. Now, going from left to right is a pretty well understood problem, and the real question is whether we can also go the other way by evaluating an inverse of the function f. This seems really tricky because of global illumination. For instance, a part of an object could be darker because there's something that's casting a shadow, but it could also be brighter because of interreflection from some other part of the scene. So basically, to do a good job at this problem, it's really not enough to just look at individual objects or individual pixels, but we have to understand how they're all coupled to each other using light. Now, inverse rendering is the central problem of computer vision, with decades of work on things like differentiable rendering and smooth rasterization. And what's special about computer vision is that there's almost always some very challenging object detection or a classification task that must be handled using machine learning, which these days usually means neural networks. And while a lot of energy has been put into things like network architectures, I would say that rendering has remained at a fairly OpenGL-style level of realism. One interesting trend is that people are increasingly looking into offloading rendering onto neural networks as well, using things like generative adversarial networks. This is more of a computer graphics talk, so the focus is a little bit different. I'm interested in solving inverse problems that are realistic, which means that the function f tends to be more complicated by accounting for things like global illumination, realistic materials, volumes, and maybe even polarized or spectral light transport. In contrast to computer vision, where it's, for example, not possible to write down a clean mathematical expression that distinguishes cats from dogs, we're in a much better situation because the underlying equations exist and they're also quite well understood. So we should be able, in principle, to do all of this without neural networks. Let's take a look at how inverse rendering could be useful. Suppose we're given a few pictures of the starfish and our goal is going to be to reconstruct a textured 3D model. Then we could create a scene containing a crude approximation of this object and optimize this scene so that it looks more and more like the reference images. The optimization will then try and match the material on the starfish, and it also uses information from the different views to extrude these little bumps on top. Now, in the case of these references images here, they were actually also rendered using a Monte Carlo renderer, so it's not too surprising that it works. But we can also run the same process on real-world objects like this pear, which has been photographed from different orientations. And the inversion is done realistically, which means that extra cues like shadows also provide information that can be used to further improve the geometry. In both of these examples that I showed here, by the way, we were modifying a directly visible object to change its appearance. But light transport is a very global process, and objects also have indirect effects on their environment. A glass panel, for example, can refract light into pretty much any caustic. And by inverting this process, we can find out what shape is necessary to create some desired caustic. Now, this problem has been studied before, but using Taylor techniques that can only solve this specific problem. And our goal for today is to really find something much more general. Anyway, this is what the process looks like. So we start with a flat glass slab, and that just lets light pass through without changing it. But that slab is really a height field, and all of those height values become part of an optimization problem. And after a few iterations of this process, we have a new height field that creates Hokusai's great wave, but only from a specific direction. And you can see that when the glass panel rotates here. In the last example, we were compressing and expanding light to create different shades of gray. But we can also mix different primaries to reproduce a color image like this famous painting by Georges Seurat. And that creates a much rougher height field. Here we only optimize the part in the image rectangle, which is why there are these random colors around on the sides of the image. Nowadays, you can buy super fancy 3D printers that can mix tiny ink droplets into the printing material as they go about their job. And one huge problem with this approach is subsurface scattering. Basically, all of these materials are very transparent, and so simply mapping a texture on an object doesn't work because it gets blurred out. And to fix this, we need to find out what configuration of ink droplets will produce an image that looks similar to what we wanted, but taking subsurface scattering into account. So this here is now a blurry version of that material. And after optimizing the result using a realistic volume renderer, we can recover some of the missing detail. Realistic inversion of light transport is really a brand new topic, and the number of things that you could try and do with it is just staggering. I find it really exciting to work on computer graphics at this time. In the past, our field has been very focused on visual effects and movies, and now suddenly there are all these new and alluring applications in other areas. Think of architecture, for example. In a building, it's usually very bright near windows and kind of dark on the inside. And the way in which this happens actually changes throughout the day and the year. So architects have to add extra electric lighting. And a good architect will think of a building a little bit like an optical system to use daylight as much as possible. And I think that we could really help architects by basically differentiating the whole building with respect to their lighting design goals and then visualizing those gradients in an intuitive way so that they can change the building. So that's the end of my motivation section. So I hope that you're motivated. Keep in mind that differentiable rendering is far from being a solved problem. And on the contrary, it's actually quite difficult to use at the moment. And there's a lot of work to be done before it becomes as practical as normal rendering. And we'll talk about some of those issues later. But let's first move on to an example problem and study that in a little bit more detail. And this example problem is really quite contrived, but we have to start with something. For example, I'll completely ignore shape optimization in this part of the talk, but we'll get to that later. So suppose we're rendering this lovely image of a T-set, but we actually don't like this rendering. It should look more like this instead. Unfortunately, we don't have that nice blue swirly texture, but only the boring gray one. And so our goal is going to be to reconstruct that missing texture, but using only this reference image here. So how do we do that? Well, first we need some way of measuring how close we are to getting it right. That's called the objective function, which takes a preliminary rendering as input, and then here measures the L2 error against some reference. This objective function could be much more complicated. For example, it could be a neural network, but let's just stick with the simple one for now. For inverse rendering, we just plug our rendering algorithm into this function, and then we search for the best scene parameters that make the objective function happy. The optimization domain is a high-dimensional space of all possible meshes, materials, textures, and so on. And this is the point where we throw up our hands in defeat and try something else because it's just too difficult. So instead of solving this impossible global optimization problem, we'll try our luck with a global one using gradient descent. And here in each iteration, we'll do a test rendering and pipe the output into the objective function, which potentially also takes extra inputs like the reference image, but it doesn't have to. And the important thing is that this objective function g just outputs a single number z at the end. And then we can differentiate this combination of f and g to figure out how we should change the scene to improve the objective. So far, so good. So what's really going to help with all of this is the chain rule. So when we're differentiating nested functions, it says that we can actually deal with the differentiation one function at a time. So we'll first differentiate the objective function, which basically measures the sensitivity on the number of the number z on this preliminary rendering y. And that actually gives us an image. And in the case of our simple L2 norm, that's just the difference of where we are now and where we want to get to. Now, although this is really a 2D image, let's think of it as a long vector which has all the pixels stacked on top of each other. And assuming that we have that, then the next step is to differentiate the rendering algorithm, which gives us a matrix that will now translate this change in image space into a change of the scene parameters. The chain rule now says that we have to left multiply the vector by this matrix to get the gradients that we need for gradient descent. Now, differentiating the rendering algorithm and doing this matrix multiplication, those are really the two tricky parts. So let's forget about everything else. So to recap, we have this gradient image that you can see here. It basically encodes how the optimizer would like to change the rendering. And this is what this image looks like in our simple toy example. So you can immediately see the global nature of light transport with gradients in the reflection on the table. And I'm assuming that this image is known. And what we have to do now is to do this matrix multiplication to transform this image containing image space derivatives into derivatives of the scene parameter, like the texture in this example. So let's talk about how to compute the entries of this matrix, and then we'll go over various challenges like efficiency, discontinuities, robustness, and so on. A really simple thing that you can do is to use finite differences. So here we would take each scene parameter and then just wiggle it around a little bit and do a test rendering to see how that changes the image. And that gives us one column of the matrix that we want. Now, there are a bunch of problems with that. First of all, knowing how much to perturb a parameter to avoid approximation and rounding errors can be difficult. Today's rendering algorithms also rely on randomness, and it's a really bad idea to compute finite differences of noisy signals. We can try and always use the same random numbers, but there are situations where that is just not enough. And finally, this is going to be kind of slow. So let's move on. A much nicer way to handle this problem is to differentiate the equations used by the simulation and use whatever comes out of that. This is called Differential Monte Carlo and was already used in the mid-60s with two concurrent works by Mikhailov in Novosibirsk, Russia, and Miller at the Argonne National Laboratories in the US. And both of them were interested in understanding how the reactivity of a nuclear reactor changes after tweaking important system parameters. And many thanks to Eugene Dion for helping track down some of these early references. So to see how this approach works, let's start by reviewing the rendering equation that's also used in our simple toy example. What it says is that the light that's traveling away from some surface arises because of one of two different things. Either the surface is emissive, for example, this table could be on fire, or light could be coming directly or indirectly from somewhere else and then be reflected by the table. Let's now differentiate the equation, and I'll use this little green partial sign as a placeholder for a derivative with respect to any of the millions of different scene parameters. And I'm going to apply it to the whole equation, starting with the first part. So here's how you can understand that intuitively. We're still looking at the same table, but we're looking at it through goggles that reveal another kind of radiation, which are the derivatives. And so this derivative radiation is still emitted from this burning table, but only when it's on fire in a differentiable way, which means that there is some scene parameter that controls the appearance of the flames. Next, we can differentiate the integral, which actually contains a product of things. And so we have to apply the product rule that will now produce several terms. So let's actually just look at the first one of these terms first. What it says is that that normal radiation, so just ordinary radiance, is converted into derivative radiation when it interacts with an object that has differentiable parameters. And the last term says that when derivative radiation that's bouncing through the scene arrives at the surface, then it just gets reflected the normal way based on the BRDF of the surface. So TLDR, there are basically two ways that derivative radiation can be created, either by differentiable emission or differentiable reflection. But then once it's created, it bounces around just like normal light. And let's now apply this idea to our example problem. We'll differentiate the rendering equation with respect to the texels of this teapot texture, and that textile has a direct influence on the scene, but only in a small patch that's shown in red here. But it also has an indirect effect on other parts of the scene, which we can determine by emitting differential radiance from this red region. So this differential radiance will bounce around in the scene, and the end result is an image that looks something like that. Now remember that our goal was to evaluate the chain rule, and for this we need to know the matrix on the right-hand side. And then our goal is to multiply this matrix with this given gradient image that expresses how the rendering should change to translate this into changes of the scene parameters. And so this multiplication is very much an image space operation. And so let's actually move to the camera's point of view to understand better how that all works. So this is what differentiable rendering looks like from the camera's point of view. We have derivatives which arise because of differentiable scene parameters, and those are shown in red. And then we have derivatives which show how the rendering itself should change, and those are shown in blue. And these two different kinds of derivatives now meet in image space, and the chain rule performs a discrete dot product of both signals to compute one entry of the gradient vector that we need for stochastic gradient descent. And so what we have to do now is to run this whole process once for every scene parameter. You can see how the texture gradient is getting filled in at the top left. And then eventually we can perform a step of gradient descent. So the texture here is quite low, whereas in practice you do this a number of times for finer and finer parameters. Okay, so just to repeat, this is really a very discrete approach. So we discretize this image into pixels, and we discretize the simulation into Monte Carlo samples, and then we run the chain rule on the end result. And later we'll show another way of solving this problem that is a little bit more continuous. So people have been using this approach for a number of years because it avoids the robustness issues of finite differences. But there's really a bear in the room that we have to talk about now, which is that this matrix we're evaluating becomes insanely huge. So with 1 million parameters and 1 million pixels, which isn't even big, we'd be talking about almost 4 terabytes of data that have to be computed using an expensive simulation. And these are rendering budgets one would expect to see for feature film animation, and we're only talking about a single gradient step here. So sometimes there are ways of dealing with large matrices by exploiting special properties, things like sparsity or low rank, but the bad news is that it doesn't have any of these properties. So let's take a step back and think about how we've used differentiation here. And to explain things, I'll be looking at a really simple example calculation where we just multiply two numbers and then we add a third one. So what we did with differentiable Monte Carlo 2 slides ago was to wiggle around one of the inputs of a calculation to see how it affected the output. But then we had to do that over and over again because there were many inputs. And this is actually a standard design pattern called forward mode differentiation. And it can be very tedious to differentiate things by hand, and a technique called automatic differentiation is often used to help out. For the case of forward mode, it's almost trivial to do this by defining a new floating point type that not only keeps track of its value, but also how much the value wiggles around with respect to the parameter that's currently being differentiated. So you just implement your program on top of this kind of type, and the derivatives will just come out magically. Okay, so in reverse mode, which is sort of the alternative version to do all of this, we instead wiggle around the output and then evaluate the chain rule in reverse to see how that affects the input. This is vastly more efficient when the function has many inputs. And in the context of neural networks, this way of running differentiation is known as backpropagation, and it's one of the key things that makes training of neural networks even possible. So it seems we were just using the wrong mode. We should have used reverse mode all along for our differentiable renderer. There's just one major issue with this approach, which is that evaluation of the derivatives now happen in the opposite direction compared to the original execution of the program. So we need some way of doing this reverse pass through the computation, which is normally done by keeping track of all of the operations in what's called a computation graph that we can then traverse in reverse after we're done. One last thing worth mentioning is that this question of forward or reverse mode are really fundamental design choices, and they're actually unrelated to whether or not one uses manual or automatic differentiation. Okay, let's switch gears a tiny little bit. So my lab's research renderer called Mitsuba 2 uses reverse mode differentiation and a just-in-time compiler to differentiate simulations on the GPU. And let me just show you a few representative lines of code to provide some intuition about how that all works in practice. So we start by requesting a 2D sample from a sample generator. Now, normally you'd expect a floating point answer, but what Mitsuba actually does is to record all of the steps that are needed to compute this value at some point later, symbolically, without executing them yet. And it's also not just computing a single sample, but a whole wavefront with hundreds of thousands to millions of samples. And then next, we transform all of these samples into rays emanating from the camera, which adds a whole bunch of extra steps to this graph, but doesn't do the actual computation yet. All of these operations pass through several layers of a vectorization library called Enoki, which provides a just-in-time compiler and what's necessary to implement automatic differentiation. Now, suppose that this camera that we're sampling has some differentiable parameters. Maybe we're optimizing its position. So in such a case, there are actually two graphs that are maintained by the system at any time. The first is the one by the JIT compiler, which keeps track of what is currently being computed. And the other one is in the Autodiff component, which keeps track of this computation graph that we'll later have to traverse once more in reverse. Eventually, we reach a point where this evaluation can no longer be postponed. So in this case, we'll be using optics to perform the ray tracing operation on the GPU, and optics wants proper rays as input. So at this point, our system compiles a fused kernel that contains everything that was queued up so far, and then hands over to optics. And I'll use this opportunity to request my favorite non-existent feature, which are PTX instructions to directly launch ray tracing calls, please. So compilation using Enoki is quite fast because it's basically just concatenating a bunch of PTX fragments and then letting CUDA deal with that. And the expensive compilation to actual machine instructions is normally just happening in the first iteration of gradient descent. We can then reuse all of these generated kernels later on. This architecture is probably not the optimal way to use a modern GPU, but what I like about it is how it enables prototyping of rendering algorithms using programming languages like Python. You can interactively design things in a Jupyter notebook with pretty okay performance. And actually, a bunch of the figures that are shown in this talk were made that way. Okay, so optics will now trace those rays, and we move on to the last line of the example. Now, sampling of the BRDF or BSDF at the surface location is actually quite tricky because parts of the wavefront have reached objects that are made of different materials. So the BSDF pointer in this line is actually an array of different elements. What Enoki does is to turn this into a vectorized method call that will launch separate kernels that run in parallel CUDA streams to handle each material. And the Autodiff backend also keeps track of this to correctly propagate differentiable information through these steps. So this is basically how Mitsuba 2 works, by wrapping the renderer into reverse mode AD and starting to record. And this works okay for smallish problems, but unfortunately, the moment that you try something a little bigger, you will run out of memory. A rendering algorithm just does such an insane amount of very messy and unstructured computations that you can maybe keep up with this recording for a second, but eventually even the largest GPU won't have enough memory. Rendering is just tricky in this way because light tends to spread out and become very incoherent. And that was the state of things last year, and it was a little bit depressing. Forward mode only worked for toy problems, and well, reverse mode also only worked for toy problems, even after some heavy optimizations using this JIT compiler and steps like graph simplification that I didn't even have time to talk about today. So what now? Fortunately, I have some good news. We'll be presenting a paper at SIGGRAPH with Merlin, Sebastian, and Benoit that I think solves this memory problem for good. And it's motivated by what is called the Adjoint sensitivity method from the area of optimal control, which is a method for differentiating things like ODEs that have a dependence on time. Imagine that we have a vector field which influences a particle. We can then run an ODE solver to tell us how that particle moves over time. Now let's say that we want to differentiate this whole process in reverse mode. That actually means that we have to run the simulation once more in reverse. But this is actually super easy here because we can just integrate that same ODE backwards once more, backwards in time, to return to where we started from. So in other words, differentiating problems where we can reverse time is almost trivial, and we can do it because of without a computation graph because of this reversibility. Now, the thing that's really unfortunate is that we don't normally have a time dimension in our renderer, and even if we added one, it wouldn't have this convenient reversibility property. On the other hand, it's kind of interesting that this method has the word adjoint in the title. And that normally means something very specific in the context of rendering. In particular, we can render an image by sending out radiance from the light sources and then propagating that to the camera, or we can start from the camera and then send an sort of imaginary kind of radiance called importance and propagate that to the light sources. And either way, the answer is the same. So remember those gradients that tell us how the image should be changed. What we will do now is to think of the camera as a kind of a video projector that radiates this image out into the scene. And if we were just rendering an image, then this is what the result would look like. But our goal is to figure out how to change the scene so that it looks more like the image that we wanted. And for this, we again have to compute a dot product of two different signals, but it's a little bit different now. And the difference is that the dot product happens on the scene surfaces, and it's a continuous integral. It's a product integral instead of a discrete sum. So this is what I meant earlier when I said that we'll make things more continuous. Okay, so this doesn't really seem to be making things any easier. So let me explain why this is such a big difference. So in practice, we'll use Monte Carlo sampling for all of this and trace individual rays, and then to project those derivatives onto surfaces. At a given intersection, there are normally just one or two local parameters like albedo or roughness influencing shading, and we know exactly which ones those are because they're the ones that are queried by the BRDF when we evaluate it. Now, what we have to do is to splat this incident energy directly into those parameters, for instance, into texels of a texture. Now, it's actually a tiny bit more complicated than that because the BRDF might be more sensitive to some parameters than others. So what we actually need to do is to backpropagate the derivatives through the BRDF to find the sensitivity of these different parameters. And this turns out to be simple enough that we can do it by hand for simple BRDFs, or basically using any kind of tool for computing derivatives and then implementing the resulting derivative shader, which you can think of as the response function of scene surfaces that now act like a giant sensor for incident derivatives. Normal radiance that's arriving at this same point also plays a role in this whole process, which I unfortunately won't have time to talk about today, but everything is explained in the paper. So that's the basic idea, but let me rephrase it in another way in case something wasn't clear. In a normal renderer, we can either propagate radiance or importance, or even both at the same time, and this can often reduce noise. But and both of these also encode color. So you'd have 3 channels in an RGB renderer coming from each side. In a differentiable renderer, we can propagate derivatives from the objects or from the sensor, and both are signed so they can cancel each other out in interesting ways. But the main difference is actually the dimensionality. There are millions and millions of scene parameters, and it's completely impractical to propagate starting from the surfaces and then towards the camera. Instead, what we should do is to go from the other side and deal with the whole product integral problem on the surfaces, at which point it becomes much easier. Here's a demo using this new method to optimize the texture of a globe that's only indirectly visible through a curved glass bulb. This is kind of similar to our toy problem, except a little bit more complicated because of this extra interreflection. We're starting out with a version of the scene where the globe has the texture of Mars and a reference image where the Earth is actually visible. And our goal is going to be to reconstruct the Earth texture on the globe while undoing all of this messy global illumination and also automatically exploiting the fact that we can actually see this globe from the front and from the back through this mirror. By the way, this kind of problem is obviously really contrived, but it's nice for testing differentiable rendering algorithms. And here you can see the algorithm running on this image and how the texture changes over time. We don't actually see all parts of this globe, even with the mirror reflection, so some parts of this reflection of the texture stay brown. And here is a close-up visualization just of the change in the texture. And here's a plot showing how quickly these different methods converge. The red one is this automatic differentiation graph-based approach in Mitsuba that I talked about. And all of the other lines are different flavors of our new method that we call radiative backpropagation. Now, one of the flavors is unbiased, and two of them are intentionally biased. And you may find this kind of surprising, but the biased ones are actually the two fast curves at the bottom, and they generally do quite a bit better. So I'll refer you to the paper for more details on why that's the case. Let's look at this other plot where we completely ignore runtime cost and just graph the convergence per iteration. What this shows is that the quality of the gradients is similar for all of these methods, again, with the biased ones having a slight advantage. And here's another example of 3D reconstruction of a smoke volume from a reference image. This is what it looks like when we run both Mitsuba 2 and this new method on the problem. Okay, so you didn't see anything happening on the left side, and that's just because Mitsuba 2 couldn't complete even a single iteration of the optimization in the whole time that it took the new method to converge. And this is the associated convergence plot. But now time is on a logarithmic axis because simulating volume interreflection just gets really expensive when you have to record a computation graph of that. And this is the last graph I'll show. So a plot comparing the speedups, so the new method over Mitsuba 2 for different scenes, sample counts, and flavors of the method. And that's quite a lot to take in, but what I just want to point out is that even the smallest bar on this slide is a 40x speedup, and we've observed up to a factor of about 1000x. Now, part of the reason why it's this much faster is because reading and writing lots of GPU memory, of course, takes time, and this new method requires essentially no memory except for a buffer into which to write the final gradients, which is really not all that different from rendering a normal image. So in summary, it's not enough to just use reverse mode automatic differentiation. We also have to exploit properties that are specific to the problem, like reciprocity of light transport in our case. And this turns the whole thing into just another kind of light transport problem with weird sensors and emitters that we can in principle solve with any kind of existing rendering technique. For fairness, I should mention that Jo Stam has been independently working on something quite similar. And after hearing about our SIGGRAPH paper, he put a snapshot of his project on arXiv that's linked above here. It's interesting because he approaches the problem from a different direction, so you might want to check it out. And that concludes this part of the talk. And in the last few minutes, I'd like to touch on two more points, which are discontinuities and robustness. So let's start by talking about these pesky discontinuities due to visibility changes. You'll find those basically everywhere in a physically based renderer, in integrals over pixels, that's the top example here, or also directional integrals involving the light sources, for instance, to compute smooth shadows, or interreflection involving the scene materials. Now, having discontinuities in a renderer is normally no problem at all during rendering, but it turns into a major issue when we now want to differentiate shapes. And the reason for this is that changing shape parameters like vertex positions is now going to move these discontinuities around in all of the integrals. So why is that a problem? Well, in the first part of the talk, we differentiated an integral, and we did that by moving a derivative from outside to the inside of the integral. And normally that's a perfectly fine thing to do, but unfortunately here now the two sides are no longer equal when we have discontinuities that with positions that actually depend on what is being differentiated. And so what we want, unfortunately, no longer matches what the differentiable renderer is going to output. So that's bad. To address this problem, we could compute the integral analytically, or we could blur things somehow so that the discontinuities go away. Now, these kinds of ideas are unfortunately not very portable to differentiable path tracers that simulate all of these different indirect effects. At SIGGRAPH Asia in 2018, Lee and colleagues presented a clever way of fixing this problem by importance sampling the edges directly. To me, this paper was a huge milestone. Basically, they were the first ones to really figure this stuff out and make it unbiased. And I'm sometimes a little bit sad when folks in other areas write surveys of differentiable rendering that don't even mention this paper. The unbiased approach for surfaces was later extended by Zhang and colleagues, first into a general theory that also supports volumes. And this year there's a paper about path space differentiation. So you can see how many people are working on making all of this stuff work that I'm really excited about where it'll be in another 2 or 3 years. Let's get back to edge sampling. So the question is this the end of the story? Well, sampling edges is actually really hard once you start to look into it. We have to find a position on the silhouette with respect to some other point in the scene. And the trouble is that every scene point will have a different set of silhouettes, and we don't have efficient data structures to find them. And because of that, the performance really tanks when there are lots of edges or when we can find the edges, but then they end up being occluded by something else because there's visibility too in addition to all of this. Let me show you a different way of achieving the same goal. And now remember that our problem wasn't really that there were discontinuities, but the fact that their position depended on the parameters that we wanted to differentiate. Our Monte Carlo samples are very discrete, and so in some sense, they don't feel the effects of these moving silhouettes. If we could just somehow suppress this motion of the silhouettes relative to the samples, then things would be fine. Or expressed in another way, if we could get the samples to move along with the silhouettes, then there wouldn't be a problem. Now, it's interesting that one thing that you can always do when evaluating integrals is to switch to a different set of coordinates. That's called a change of variables. And that's actually what we will do. We will find a new set of coordinates that moves along with the discontinuity and then just compute all of the integrals there. And it turns out that we can find such a change of variables by tracing some test rays to sort of feel how things are moving and then constructing a reparameterization based on this information. That's the basic idea. And there are a few more steps needed to really get this to work in a fully general setting, which are a little bit too detailed for this type of talk. So I'll refer you to the SIGGRAPH Asia paper that explains everything in detail. And here are some visualizations of the resulting gradients for rotation, translation, and scaling of an object. The middle column is the reference from finite differences. The right column shows what the gradients look like when we don't do anything special. You can see that they're essentially 0. And the left column is this new change of variables approach. So you can see that it matches the reference. All of this also works for indirectly observed discontinuities like glossy reflections of an object, shadows, and even refraction. And the nice thing is that we don't need any fancy data structures to implement this idea. So all of it is based on ray tracing, which is very optimized these days. Because we don't have to rely on a tricky edge sampling operation, variance of the gradients also tends to be lower for complex objects. Here you can see an equal time comparison between edge sampling and this new change of variables idea. And when we subdivide the teapot, our method produces basically the same gradients because it just uses ray tracing and doesn't care about how things are tessellated. Of course, there are some downsides as well. In particular, our method contains approximations that add some bias to the gradients. As you can probably imagine, we're really interested in putting everything together now. So we want to have differentiable edges with radiative backpropagation and then to implement that on top of the just-in-time compilation approach in Mitsuba 2. Let's go to the last point, robustness, and then I'll wrap up. And this is the slide where I currently don't have any good answers. Differentiable rendering resembles training of neural nets. But the thing with neural networks is that you can just initialize them randomly. And for reasons that nobody really understands at the moment, the high-dimensional geometry of minima and saddle points causes stochastic gradient descent to find solutions that are pretty good. The same definitely cannot be said for differentiable rendering. We have to start with something that's already fairly close to the end result, or things will just explode. It would be really cool to be able to start from an empty scene or even a random one and then just create something from scratch based on an image reference, but we're just not there yet. Right now, we're using simple loss functions like L1 or L2, and people have also tried combining differentiable rendering with neural networks like VGG. So what's really the best thing to do there? And should we even be rendering images or directly to some other kind of basis functions that's maybe superior for optimizations? Some scene representations lead to very non-convex optimization problems. What we already know is that triangle meshes tend to be bad and implicit representations are more robust. But is there more to it? And what's really the best that we can do? Right now, we're also often tweaking multiple things at the same time, like running gradient descent, and then at the same time increasing the resolution of textures to provide more degrees of freedom. All of this seems kind of hacky, and I wonder if there isn't maybe a better way. So as you can see, there's plenty of work to do, and I think that makes this a really exciting time to work on these topics. And that's it for today. I'd like to thank my brilliant students and collaborators that have made these projects possible. I'd like to especially highlight Merlin Nimier-David, Guillaume Loubet, Benoit Ruiz, Sebastian Speyerer, Delio Vicini, Tizian Zeltner, and Nicolas Holzschuh. And I'd also like to acknowledge the artists, including my wife, Olesia, who designed 3D models that I used in this presentation. And I'll close by saying that I'm always looking for excellent PhD students and postdocs. And if this kind of stuff is interesting to you, then we should definitely chat. Thanks for your attention, and I'd be happy to take any questions now.